I want to talk about how drugs are made, because once you understand how drugs are made, you'll understand why they don't have cures for diseases. So every single day, billions of people, they swallow a pill, and almost nobody knows how it was actually made. Like, how did someone figure out that this specific arrangement of atoms, this exact molecule would fix a problem in your body? Like, how was that actual pharmaceutical drug made? Because here's what most people don't realize. The majority of drugs that you've ever taken, it started as something alive. And whether it was a fungus growing in a dirt, whether it was bark stripped off a tree, whether it was a chemical weapon produced by bacteria engaging in like a microscopic war and so on, but it started as something alive. And the ground that you're standing on right now, it contains more drug candidates than every pharmaceutical lab on earth combined. So today, I'm going to walk you through the entire process of how drugs are made. From the first moment that a scientist notices something in nature, all the way to the pill in your medicine cabinet. And then I'm going to tell you why this whole system has a massive blind spot, one that probably explains why we can't still cure diseases like MS, which is what I have, and diseases like Alzheimer's, other autoimmune conditions, and all that. So you don't really need a science degree to follow this. I mean, you just need some curiosity. So first off, what is a drug? Like, what is a drug really? So before we talk about how drugs are made, you need to understand what a drug actually is. A drug is just a molecule that changes the way something works inside your body. Your body is basically a massive city of microscopic machines, and you have proteins that act like factory workers. They're building things, they're breaking things down, they're sending messages, they're opening and closing gates. When you're healthy, all these machines are working fine. And when you're sick, one of those machines are broken. One of the machines, it's broken. So maybe it's stuck in the on position. Maybe it just won't stop. Maybe it's shut down completely. Maybe it's building the wrong thing, but that machine is broken. And a drug is a molecule designed to walk into that factory and fix that broken machine. So it might like jam a wrench into the gears to stop the machine that just won't quit. It might flip a switch and turn one back on. It might act like a decoy sitting in the machine's seat so the real troublemaker can't get in. The entire challenge of making a drug is this. You need to find or build a molecule with exactly the right shape, size, and electrical charge to interact with one specific machine, and only that one specific machine. So out of the tens of thousands of machines that are running inside of every single cell, the molecule needs to interact with just one. So imagine trying to design a key that opens one specific lock in a building with 20,000 locks. That is drug design. So remember that image, one key, one lock, because later on I'm going to show you why that way of thinking is both the greatest strength and the greatest weakness of modern medicine. So where do drugs come from? Here's something that will surprise most people. The majority of drugs in modern medicine do not come from a lab. They come from nature. They came from nature. They came from plants. They came from fungi. They came from bacteria, even animals. So scientists, they went treasure hunting in the natural world, and they found molecules that evolution had already perfected over millions of years. So let me give you 3 examples. Example number 1, aspirin. Aspirin. For thousands of years, people, they chewed the willow tree bark when they were in pain. It was like ancient Egyptians did it. They did it like in 400 BC. Nobody knew why it worked. They just knew it worked. Like just chewing this willow tree bark, it just worked for their pain. And in the 1800s, a chemist, he isolated the active ingredient, a compound called salicin. In your body, it breaks down salicin into salicylic acid. And that molecule, that's the molecule that kills pain. It blocks a machine in your cells called COX, and like COX. So normally when you get hurt, COX, it converts fatty acids from damaged cells into molecules called prostaglandins. And these are like your body's alarm system. It's your body's alarm system. So they create inflammation, pain, fever. If you block COX, then you turn down that alarm. The problem is that the salicylic acid, it destroyed your stomach. So they're like, okay, this acid, well, it destroys your stomach. So in 1897, the chemist at Bayer, his name was Felix Hoffmann, he made one small tweak. He stuck like an extra chemical group into onto the molecule, and that's it. Just one chemical group. That's it. Just one small tweak. And that one modification, it resulted in aspirin. And that little group, it turned out to be that little extra group. It turned out to be just a weapon. It permanently disables the Cox machine by physically gluing itself to it. So most drugs, they sit in a machine temporarily, but aspirin, it breaks that machine for good. So one tiny tweak, like to a molecule, a tiny tweak to a molecule from a tree bark, it created one of the most important drugs in human history from a tree bark. Let me give you another example, statins. Most people don't know this. Statins, it came from the 1970s where there was a Japanese scientist named Akira Endo, and he had an idea. He knew that fungi in soil are at constant chemical warfare. They produce toxic compounds to kill the competitors. They're just trying to kill each other. So he thought, well, what if some of those compounds happen to block the same chemical pathways in humans? So after testing over 6,000 fungi, he found one that produced a molecule blocking a machine in your liver called HMG-CoA reductase. And this is like your liver's cholesterol assembly line. So this fungal molecule, it looked just like the raw material that the machine normally grabs, and it tricked the machine into latching onto it. But the machine, it couldn't process it. So it just sat there clogging everything. So cholesterol production just dropped. He just figured this out. That became the basis for lovastatin. This was like the first statin. And eventually chemists, they used the natural molecule as a blueprint to build other versions, other statins. And it's all because one scientist looked at fungus and he asked the right question. I'll give you another example, antibiotics. So beneath your feet, there's a war going on. There are trillions of bacteria and fungi in the soil, and they're fighting for territory, and their weapons are chemicals. They use molecules designed for their neighbors. They're trying to kill each other. This war has been going on for millions of years, by the way. They're producing extraordinary chemical, like an insane arsenal of chemicals. And almost every major antibiotic that we have was stolen from this war. Penicillin, well, it's a weapon made by mold. It blocks the machine bacteria used to build their cell walls. And without this wall, bacteria, they literally just burst. And because human cells, they don't have this type of wall, penicillin, it kills bacteria without hurting us. So the same thing happened with tuberculosis. The golden age of antibiotic discovery, it was basically humanity raiding an underground weapons depot that evolution had been stocking for ages, for eons. They've been stocking it forever. We just raided it. And we're like, okay, this works. So here's like the three ways that scientists find a drug. So nature is full of molecules that interact with biological machines, but there are billions of possibilities. So how do scientists narrow it down? How do they actually find the drug? So method number one is just brute force. They just try everything. So pharma companies, they have warehouses containing millions of different molecules collected over decades. And when they want to find a drug for a new target, robotic systems, they test every single compound. So they go in, they say, well, this molecule 437, 291, does this stick to the broken protein? No? Okay, next. How about molecule 437, 292? Oh, that does something? Okay, flag it. Let's move on. And they keep doing that. It's just brute force. So this is called high throughput screening. And they do hundreds of thousands of tests per day. Most of it does nothing. A small fraction shows activity. And when it shows activity, those are the starting points. So that's method number one. Method number two is rational design. So it's like building the key for the lock. So if you can see like the exact 3D shape of the broken machine, then you can design a molecule to fit into it. So it's kind of like having a picture of a lock that's zoomed in so close that you can see every little ridge, and then you create a custom key to match that lock. So scientists, they analyze the electrical charge, its shape, its water repelling regions, like where they are, where hydrogen bonds can form. Computers, they simulate millions of possible shapes to find the best fit for that. So with this method, it's about building the key for the lock. Then method number three, they steal from nature, basically, and then they improve it. So this is what they did with aspirin, it's what they did with statins, but it goes like a lot further. So one of the most important cancer drugs ever, a brand named Taxol, Taxol, It came from the Pacific yew tree bark. It freezes the internal scaffolding cells use to divide. So a cancer cell, it tries to split in two, but it can't, and then it just dies. And so this is where like a lot of different ones come from, like was it vincristine? It came from a flower. Rapamycin, it was found in soil bacteria. Evolution is essentially the original chemist. And those are the three main ways. Just brute force, they just try everything. Number two, they build a key for the lock. Number three, they find it in nature. Those are the main ways that they're finding these molecules to actually build the drugs. Now let's get to the craft, like refining the molecule. So you found a molecule, they found a molecule that does something interesting. It doesn't matter where it came from, but they just found this molecule, okay? Does something interesting. What you have right now is a mess. It sort of works, but it's weak. It might be toxic. Maybe your stomach might dissolve it. Your liver might destroy it. This is where the real art of drug making begins. So when you swallow a pill, it goes straight to your liver, and your liver tries to destroy it immediately. So drug design isn't just about fixing a machine, it's about surviving the gauntlet to get to the machine in the first place. So finding a molecule that works is only 10% of the job. The other 90% is making it work inside a human body. This stage is called medicinal chemistry. So essentially these people, they're molecular sculptors. They modify the starting molecule one atom at a time, testing each different version. So maybe they swap out like a hydrogen atom for fluorine. Maybe fluorine is nearly like the same size, but it completely changes the molecule's electrical properties, and it makes it much harder for your liver to break down. So that one swap, they swap something out like that one swap, maybe it doubles the drug's lifespan in your bloodstream. Or maybe they add a small chemical group. Maybe it turns from a weak handshake into a death grip. Or what if you like flip the molecules like mirror image. So this is like an interesting one, to where a lot of molecules, they come in, let's say, a left-handed and like right-handed versions. Like people don't know that there's like a left-handed version and a right-handed version of molecules, just like your hands. They're mirror images that can't really be stacked on top of each other. If you try to stack your hands on top of each other, it doesn't work. And so sometimes one version is a miracle drug and the mirror is a poison. So it's interesting. A team, they synthesize about, 2,000, 5,000 versions over like 2 to 3 years. So they're playing around to create tons of different versions pretty much. And each one is handcrafted, it's purified, it's analyzed, and it runs through tons of tests. And here's what makes it so hard. All the properties are connected. So does making it stick to the target make it better? Well, it might make it stick. It might also maybe stick to things that you don't want it to stick to. So this will cause like certain side effects. Maybe if you make it survive longer in the body, maybe it becomes too toxic. Make it dissolve in the blood, it may not cross into the cells. So it's like engineering a car that's faster, lighter, safer, cheaper, and more fuel efficient. But if you improve one thing, something else gets worse. So it's interesting how they're doing this. And that's why for every 10,000 molecules that start in a lab, only one actually makes it to your pharmacy. And the rest, they fail because they're probably too toxic, maybe they don't work in humans, or they just disappear from the blood too fast. Now, the other kinds of drugs, biologics, everything so far is about small molecule drugs, tiny chemicals that you swallow as a pill. But there's a whole other category called biologics. Instead of building a small key, scientists, they engineer large molecules, usually proteins, made by living cells. So scientists, they figured out how to custom design them to grab any target they want. So if they want to block an inflammation signal, you design an antibody that grabs it. If they want to mark cancer cells for destruction, you design one that sticks to a protein only on the cancer cell surface. The catch is that biologics can't be swallowed because your stomach is just going to digest it. So they have to be injected. And manufacturing them, it means growing living cells in these massive steel bioreactors, feeding them nutrients, harvesting the antibodies, and then purifying through multiple filtration steps. It's more like brewing than chemistry, to be honest. And here's where drug making is essentially going. So the newest drugs, they don't fit the old categories. They're rethinking what a drug can be. And these are the mRNA drugs. So instead of giving you a molecule that fixes a broken machine, you give your cells the instructions to fix themselves. So it's kind of like emailing someone a blueprint instead of just mailing them the replacement part. And you can change what gets made just by changing the instructions. That's what all this mRNA stuff is. So something is essentially sending the instructions, and it's easier than shipping the finishing product. But here's the blind spot. Here's why this isn't enough. So you understand how the drugs are made, okay? So now let's get to the part why this isn't enough. I need to tell you something that the pharmaceutical industry, they don't really talk about. The entire system was built on one assumption, that diseases are caused by one broken thing. And if you fix that one thing, the disease goes away. For a lot of diseases, that assumption is wrong. So remember the key and lock metaphor from earlier? One molecule, one target, one fix. For some diseases, it works great. If you have a bacterial infection, great, just kill the bacteria. Boom, one target, one solution. Acid reflux, hey, block the acid pump. Headache, block the pain signal. The simple problems with clear targets, that's what that works for. But what about diseases like MS, Alzheimer's, Parkinson's, damn near every autoimmune disease, chronic inflammatory diseases? These aren't one lock problems. These are 1,000 lock problems, and all the locks are connected to each other. So imagine like this, I created this homelessness analogy. So let me put it this way. Imagine a city has a homelessness crisis. The current drug making approach is like sending a team to one specific street and removing all the homeless people from that street. The street looks better. It definitely looks better, and you can measure the improvement. You can publish a paper on it. Oh my goodness, we removed everybody. We published a paper on it. Look, it looks great, but you haven't solved homelessness. You haven't addressed why people are becoming homeless. You haven't built housing. You haven't fixed the economic system. You've cleaned up one visible symptom and called it progress. That is what most drugs do for complex diseases. They clean up one street, but the entire city is broken. Take multiple sclerosis, for example. In MS, it's not just the immune system attacking myelin. It's the breakdown of the gut barrier, a breakdown of the brain barrier, a lack of microbes that produce butyrate. It's a bioenergetic problem. It's a toxic environmental problem, so your cells, they can't be repaired. It's a 1,000 problem disease. It's not one broken lock, it's a broken city. So if you look at the drugs that we have, let's say for MS, almost every single one targets one node and it's in the web of problems, just one thing. One drug depletes maybe a type of immune cell, another blocks immune cells from crossing the blood-brain barrier, another traps immune cells in your lymph nodes so they can't reach the brain, another reduces oxidative stress through a single pathway, and they slow the disease down a little bit, but none of them ask, why did the immune system go rogue in the first place? None of them fix the gut signals that are mistraining the immune system. None of them restore the environment that will let repair cells do their jobs. None of them clear the debris that physically is blocking repair. They're managing the fire, and nobody is asking who keeps lighting the matches. It's a one molecule, one target, one trial, one approval process. That's why the system is stuck. So here's the deeper problem, and this is the part that nobody really talks about, thinks about. The one molecule, one target model isn't just a scientific limitation. It's a structural one. So the entire system is built around it. Clinical trials, they test one drug against one placebo. That's how you get FDA approval. That's how you get a patent on one specific molecule. That's how investors get their return. The whole pipeline from discovery to the pharmacy shelf is designed for single interventions. But what if a disease needs 5 interventions all at once? What if you need to fix the gut? You got to calm the immune system. You got to support the repair cells. You got to reduce the toxic environment, and you got to clear the debris simultaneously. And if you don't do one of them, all of them fail at the same time. That's not one drug. That's a systemic level intervention. And the regulatory framework, the patent system, the funding model, the clinical trial design, none of it is set up for that. We built a system that's brilliant at finding a one key for one lock. We built a system that's great for that. Then we discovered that the hardest diseases aren't locks at all, they're cities. So what do we do about it? Now, I don't want to just leave you with a problem here because there are people like thinking about this differently. So researchers, they are mapping the connections between the gut microbiome and the immune system. They're tracing how bacterial metabolites, how they travel, like they go from your gut, travel to your brain, and they either promote or prevent inflammation. There are people working on this. They're identifying like specific pathways that connect digestion to immunity, to neurological health. And some scientists are trying multi-targeted approaches instead of just a one molecule hitting a one lock. Like they're trying things. So it's just harder to prove. You can't easily isolate which piece is doing what. In clinical trials, they want clean, single variable experiments. But biology is a web. It's a mismatch between how we test drugs and how diseases actually work. It's one of the biggest problems in medicine. But science, it's catching up. The tools are getting better and the conversation's shifting. Hopefully keep shifting. The next breakthrough in medicine is not going to be a single molecule. It might be to think in systems, to learn to think in systems. So the next time you pick up a pill bottle, think about what you're holding. That tablet, it might contain a molecule that was inspired by a tree, or a weapon that was stolen from soil bacterium fighting a war that no one can see underneath your feet, or a molecule that a chemist, they spent 3 years just sculpting atom by atom. It's impressive, but also understand what it probably is not. It probably isn't a cure. I'm pretty sure it's not a cure. Not because the science isn't amazing. It is amazing, but it's not a cure because the hardest diseases aren't one broken machine. They're broken systems, and fixing a system requires a different way of thinking than fixing a machine.